Okay, this is the second additional presentation that I've done on network math. In this presentation, we'll be talking again about network address, broadcast address, talking about specifics or identifying host address, and we will talk about subnetting. As far as subnetting goes, we will be talking about variable length subnetting and also creating subnets of equal size, two things that we have talked about before. So for the first example, I want to start out with variable length subnet mask. And what we have is we're originally given a 172.20.0.0/16 network to work with. And what we want to do is use variable length subnet mask, sometimes referred to as classless interdomain routing or CIDR, to create networks for the four networks shown here. Network A has 34 hosts, Network B has 18, Network C has 12 hosts, and Network D needs to have 2 hosts. So the first thing we do with variable length subnetting is we order the subnets from the largest to the smallest if they're not already ordered that way. In our case, when I made this example, I did order them from largest to smallest. So for Network A, what we need to look at is we need a network that has 34 or more usable hosts. And of course, the equation we solve is 2 to the n minus 2, where n is the number of host bits that is greater than or equal to the number of host addresses we need. So 2 to the n minus 2 greater than or equal to 34. The correct answer is n equals 6. 2 to the 6 equals 64. So we are going to have a little waste in here, but we are going to minimize that using variable length subnetting mask. For network B, we need to solve usable host greater than or equal to 18. The smallest value of n that will do that is 5, because 2 to the 5th is 32. On network C, we need to solve that equation for greater than or equal to 12 usable addresses. The smallest value of n that will do that is 4, because 2 to the 4th is 16. And finally, for network D, we need to end up with 2 usable hosts, and the value for n in that equation is n equal 2, because 2 squared equals 4 minus 2 exactly equals 2. So there will be no waste at all in this subnet. So what we need to do is go through network by network and figure out what the network address and broadcast address is going to be. So if we do that for network A, we decided that we needed 6 host bits to do this. That is a /26 subnet mask. The reason that it is 26 is because we have the 32 bits of the IP address. We're going to use the last 6 for host bits. So the subnet mask is /26. The network address is going to be the beginning of the network we were given. So it's going to be 172.20.0.0, but it's going to be /26 instead of the original /16 we were given. The next thing we need to do is figure out the broadcast address. And what the broadcast address is going to be is the last 6 bits are going to be set to 1, because that is our, this is a broadcast address. And then all the rest will be whatever we had before. So that 6 that we needed is there with all the host bits set to 1. If we convert this last octet back into decimal, we're going to get the broadcast address for network A is 172.20.0.63. Now then, for network B, the network address is going to be 172.20.0.64. How do we know that? Well, 64 is 63 plus 1, and the significance of the 63 is that was the broadcast address of the previous subnet. So the network number of the next network is going to be 1 higher than the broadcast address. Now then, if we convert the 64 into binary, we have this value. We needed 5 host bits, which means it's a /27. So a /27 is going to be divided where the red line is on the screen. To figure out the broadcast address, what we need to do is keep the 010 because that's part of the network address, and the last 5 bits need to be set to all ones. Once we do that and convert that to back decimal dotted notation, we get 172.20.0.95. So that is the broadcast address for network B. For network C, we go one higher than the broadcast for the previous subnet, so that's going to be 96. Again, that's 95 plus 1, where 95 was the broadcast address of the previous subnet, which was network B. If we convert 96 to binary, this is what we get. In the case of network C, n was equal to 4, so we needed 4 host bits, which means we need a /28 subnet mask. And I'm just showing here with the red line that 4 of that last octet, the first 4, are part of the network address, and the last 4 are the host portions. And so if we preserve the network portion of this, the 0, 1, 0, and then we set all the host bits to 1, which we're showing here, and convert that back to decimal dotted notation, the broadcast address for network C is 172.20.0.111. And finally, for network D, the network address is .112. Because the broadcast for the previous subnet was 111, we add 1 to that, and we're going to get the 112. 112, this is its representation in binary. We need 2 host bits, which are going to be shown with 6 as part of the network, 2 part as the host. If we then take the 0, 1, 1, 1, 0, 0, and then set all the host bits to 1, this is going to be our broadcast address, and converting that last octet back into decimal is going to tell us that the broadcast address for network D is 172.20.0.115. So that's just another example of how to go through and do variable length subnetting mask. The next few examples are going to be, I'm going to give you an IP address and a subnet mask, and can we identify whether this is a network address, a broadcast address, or a usable host address. So example 2 will start like this. We have an IP address, and it's a /21 subnet. So what we need to do is figure out what portion or what is the host network address. So a /21 takes us into the 3rd octet. So the 3rd octet is the only one that we need to really worry about. So in the IP address we have a 21. In the subnet mask, a /21 is going to be the first 5 bits set to 1, the last 3 set to 0. So it's going to be the equivalent of a 248 subnet mask. And if we use our knowledge of what a subnet mask does, that says that the 172.10 and the first 5 bits in the 3rd octet are the network portion of the address. And then where we have zeros in the subnet mask, which would be the last 3 bits of the 3rd octet and all of the 4th octet, if we go through and do a bitwise AND on these, we're going to get 0, 0, 0, 1, 0. So anything ANDed with 1 is itself. So that portion of the 21, the first 5 bits, just come down as is. and anything ended with 0 is going to be 0. So we end up with 0, 0, 0, 1, 0, 0, 0, 0. Converting that back to decimal is 16, which means our address is 172.10.16.0. Now then, the next question is, what is the broadcast address? So again, working with the third octet, we had a division point where the red line is shown. The network portion 0010 is as it was before. And the way we get the host address is by setting all the host bits to 1. So in that third octet, we end up with 23. And of course, the fourth octet is the host portion, so that is all going to be 1s. So when we do that, 172.10.23.255 is going to be the broadcast address. Now then, this example is, I give you an IP address. I may have misspoke on example 2. That was find the network address and broadcast address like we've done before. This one and the next couple are going to be, here's an IP address. What type of address is it? So we have 10.10.5.10 and a /22. That means, again, the division point is in the third octet. So what happens is we have this third octet converted to binary. We have the subnet mask converted to binary. Using the subnet mask, we know that is the division point between the network and the host. So what happens is, for this to be a network address, the 2 bits on the host on the top line would need to be 0, 0, and everything in the third octet would need to be 0. So that is not true, so this is not a network number. For this to be a broadcast address, all the host portion would need to be 1. In the last 2 bits of the third octet, that is not true, and 10 does not equal 255. So this is not a broadcast address, so this means that this IP with this subnet range has to be a host address. Okay, doing a different example, given 10.10.5.31 with a /27, we need to go through and kind of examine this. A /27 subnet mask means we're working in the fourth octet. So what we would have is, this is the representation of 31. It is 0, 0, 0, 1, 1, 1, 1, 1. The subnet mask of /27 is 3 bits into the last octet, and then we would have remaining bits set to 0. So this is the division point between the host portion and the network portion. So looking at this real quick, we see that the host bits, it's very easy to see that they're all set to 1. So we know right offhand this is a broadcast address. Okay, example 5 is we have a 10.10.7.255 with a /20 subnet mask. A /20 subnet mask means we're going to be dividing in the third octet. It's real tempting to look at it and see that it ends in 255 and say, hey, I bet this is going to be a broadcast address. Converting this to binary, since this happens in the third octet, I went ahead and converted the third and fourth octet. We still see a bunch of 1s down there at the end. The subnet mask is 1, 1, 1, 1 in the third octet. Last 4 bits 0. The last octet, all 0s. So when we look at the subnet mask, this is the division point where we change from a string of 1s to a string of zeros. And if you notice really quickly, the host portion is not all ones. It is except for the very first bit. Likewise, it is not all zeros that it would need to be a network number. So this one ends up being a host address. Okay, example 6. We're going to take a /8, what was traditionally a Class A network, 10.0.0.0, and we want to subnet this so that we have 800 subnets that are equal size. So we haven't solved a problem where the number of subnets is quite so large. But the process is exactly the same. How many bits do we need to borrow? And I will ask, what is the formula we need to use when we're dealing with subnets? And that is 2 to the n is greater than or equal to the number of subnets we need for the largest value of n. So if we solve this, the answer is 10. 2 to the n is 1024, but the fact and the important information is we need to borrow 10 host bits. So we started with a /8 network, and when we borrow 10 bits, our subnet mask is going to become a /18. So what we have is going to look like this. The 10 in green is the original network portion we had. These S's in red are the subnet bits. So notice it's all the second octet. And it expands over in 2 bits into the third octet, which I don't think we've seen that happen before. And the remaining 6 bits of the third octet and all 8 bits of the fourth octet are what is going to become the host bits for our new subnet. Now then, we've talked about this, but I think this might be a good way to show it. What happens is for these red subnet bits, we basically count in binary starting at 0, and in this case it would go up to 1023, 2 to the n minus 1. So what we're going to do is we're going to have a new subnet 0. And the reason it is subnet 0 is notice that all the subnet bits are 0. Subnet 1, we're going to set those bits to be the value 1. So 9 zeros followed by a 1. The leading zeros don't factor into anything. So this is the binary representation of the number 1 in 10 bits. If we go to subnet 2, we set that value to 2. Subnet 3, it's set to 3. Subnet 4, it's going to be 100, which is the binary representation of 4. And this will go all the way up to all 10 bits set to 1, which again equals 1023. So with this information, we'll go back and look at these first 5 subnets and figure out what is the network address and what is the broadcast address. So for subnet 0, this is what we had in our chart. As always, to get the network number, we set all the host bits to 1. So if we do that, we're going to get 10.0.0.0, again /18, because we are subnetting the 10 subnet. To get the broadcast address, all these places that we have black underscores would need to be set to 1. And when we do that, we would get 63.255. So we're basically using the basic easiest thing to remember. Network address is all host bits set to 0. Broadcast address is all host bits set to 1. Subnet 1, ends with the 1 down on the end. To get the network address, we set all the host bits to 0, which would give us 64 in that third octet and 0 in the last octet. And if we set all the host bits to 1, that would give us 127.255. So that's the network address and broadcast address for subnet 1. Of course, all the usable host addresses would be from 64.1 to 127.254. So one more than the network address and one less than the broadcast address. Doing the same thing for subnet 2. If we set all the host bits to 0, this is going to be 128.0. If we set all the host bits to 1, it's going to be 191.255. So there's the information for subnet 2. Likewise, on subnet 3, we have 1, which is the binary representation of 3. If we set the host bits to 0, we're going to get 192.0. If we set all those host bits to 1, we're going to get 255.255. And this might be a little interesting because we have two 255s there. If we move on to subnet 4, where we have 100 representing that 4, if we set all the host bits to 0, we get a network address of 10.1.0.0. So you can see changes are happening now in the second octet because that 1 from the binary representation of 4 has moved over into that second octet. Now then, if we set all the broadcast address to 1, we are going to end up with 10.1.63.255, and of course the new subnet mask of /18. So there were 6 more examples of various types of network math.